recorded. Okay. 11.5 alternating series test. So we have alternating series test have saying if a series is in this form, series from n equal to 1 to infinity of -1 to dn minus 1 bn, or basically you just take the absolute value of so bn is kind of like the positive part in the series. So if you have that series that satisfies the absolute value of a series, so like the sequence, the n plus 1 term in the sequence, 0 is smaller than or equal to the absolute value of n plus 1, a to the n plus 1 term, and smaller than or equal to an. So basically, when you have an alternating series, you pick whatever is the term here, the sequence, and then you find what is the n plus 1 term and the n term, and make sure that it satisfies this condition. Then if you have, and then if the second condition is that if you have limit of n approaching infinity of bn is equal to 0, then the series is convergent. And this actually is better if we look at the examples and instead of talking about bn and an like this. But this is the general form, just to get you guys like reminded if you forget what are the conditions that we need for alternating series test. In this sessions, we also have another one called alternating series estimation theorem. So this one is the theorem allowing us to estimate what is the n partial sum that when is the n partial sum that we calculate. So say we want to quantify Sn, but we approximate it by finding maybe like S16 or like S5. So we quantify what is the error from the n partial sum from this value, and the error would not be like an exact difference from the n partial sum, but it can give us like a general idea of like how far is it away from the actual nth partial sum. So say if S is the sum of a convergent alternating series, then you have, this is the error. So the magnitude of the error is smaller than or equal to the bn plus 1 term. So all we call is the absolute value of a of the n plus 1 term in the sequence, which this is the absolute value. Again, we're going to see that in the example. Some of the problems that you might be asked in this sections is find the minimum numbers of terms such that the error is smaller than or equal to some value. First of all, you have to prove that it is a convergent alternating series using the alternating series test. I'll just call this one ASD from now on, so just save your space. And then use the alternating series estimation theorem. So let's do that in the example. The first example is practice problem 1A. And as I always say, I have like a bunch of practice problems. And especially when it's this week is the week right before the exam. So I'm going to have a lot of practice problems. So kind of like also exam practice problems included. So you guys can work on it this week and maybe email me whenever you finish, maybe like before the sessions next week, so that I can, pick out maybe some of the questions either in mine or in the practice exam. Usually I just pick in the practice exam because it's going to be closer to your actual exam. But if you want me to like maybe solve some of the problems in my practice problems, that's completely fine. Just make sure that you guys email me or do the practice exam or like do both. Then I'll be able to pick out the problems. So the first example, evaluate the convergence of the series. So the series is sine of n plus half pi over square root of n plus 2. And yeah, and then so we're doing alternating series test. And again, when we have sine and a polynomial, usually the way that I always say that is that you should write down some of the terms to see what exactly is it looking for. So if you write down the terms, I'll write n equal to 1, 2, 3, 4, 5. So we're gonna have this one is sine n plus half pi divided by square root of n plus 2. So this one is going to give us, when n equal to 2, it's going to be sine of 5 half pi, which is sine of pi over 2. And it's going to give us 1. Hang on, this should be 2, 3. So this is n. 1, 2, 3, 4. So n equal to 1 is sine of 3 half pi, which is negative 1 over square root of 3. And you have 1 over square root of 4, negative 1 over square root of 5, and so on. Therefore, the train here, like this series, can be represented as negative 1 to the n. So negative 1 to the n over square root of n plus 2. So that is the kind of like the other series, and this is clearly an alternating series. So we're gonna use the alternating series test. So the two conditions of alternating series is, first, when you take the absolute value, 0 is smaller than or equal to the absolute value here. So we're gonna identify Bn is 1 over square root of n plus 2. Then you need the n plus 1 term, which is n plus 1 plus 2, which is 1 over square root of n plus 3. And clearly, this one we see that is smaller than or equal to n plus 2, 1 over square root of n plus 2, which is this I would say this is the Bn plus 1 term, and this one is Bn term. So one condition is satisfying. The other one is where you have limit of n approaching infinity, 1 over square root of n plus 3, square root of n plus 2. This one is equal to 0 because it's 1 over infinity. Therefore, the series is convergent by, I will say convergent by alternating series test. So I would say this one is really obvious, and it's not that challenging, but this is like the basic of all the alternating series. It's not hard with alternating series, but make sure you guys understand the conditions that we need to satisfy so that you guys don't miss anything. Before I go to the next example, is there any question with this one? Okay, if there's no questions, I'll go to the next example. The first half means is, yeah, it is true that it is decreasing, yeah. And then this is the way that you're gonna prove it. Yeah. Sorry, I put it in the mathematical symbols because I thought that you guys it's gonna work better for you guys. But yeah, I should have said it's a decreasing series. True, but I mean sometimes you don't need to take the derivative. Like in this case, it's really easy and very clear. Derivative is definitely one way, because if you remember integral test, that was the method I used. So to prove that a series is decreasing, you can either take the derivative, as I say in that sessions, or you can do it this way, comparing like the denominator. Of course, this case is only applicable for, fractions, but derivative will work everywhere, right? But that's cool. Let's go to the next example. It's example 2, which is practice problems 2C as well. Find the minimum number of terms must be added so the sum of a series is of error smaller than or equal to 0.008. So we say, first of all, if we want to use alternating series estimation theorem, we have to prove that this alternating series is convergent. And the way that we're going to do it is, again, we're going to use alternating series test. So Bn here is 1 over n cubed. So we're going to we have 1 over 0 smaller than or equal to 1 over n plus 1 cubed smaller than 1 over n cubed. Now, then we have the second condition, limit of n approaching infinity. 1 over n cubed is 0. Therefore, we have this series, negative 1 to the n cubed, is convergent by alternating series test. Now we use the alternating series estimation theorem. It's saying if you have a convergent alternating series test, then the error is equal to, it's gonna be smaller than or equal to the bn plus 1 term. So this one have to be smaller than or equal 0.008 based on what is given. The b of the n plus 1 term, which is 1 over n plus 1 cube, smaller than or equal, this one is 1 over 5 thirds. So I'm just rewriting 0.008 as 1 over 5 thirds. And how you know that? I would say use your calculator, or just like you can rewrite this one as like a over 1,000, right? And then when you simplify it, it's gonna be 1 over 125, which is right there. If you actually solve for this one is going to give us n bigger than or equal to 4. So when you estimate the n partial sum using S4, the error is going to be smaller than or equal to 0.008. So is that clear to you guys how we're gonna use alternating series estimation theorem? Okay, I'm gonna go ahead and get to 11.6. So I would say, because this week I don't really have like massive example like last week, because I look at the lecture notes and I feel like Dr. Tasha did a lot already, and I would leave that to the practice problems, because from this part of the exam, especially, I would say a big portion of the exam is going to asking you guys about absolute convergence and then conditionally convergence. And so I think the best way is that you guys work on it on your own and figure out your own mistake, because everyone's mistake is different. So I want you guys to work on it a lot before working on the math practice exam next week. So 11.6, absolute convergence, ratio, and root test. So absolute and conditionally convergence is defining at, so you have a series. It is absolutely convergent if the series formed by the absolute of every single term in the sequence is convergent. It is conditionally convergent if the series itself is convergent but not absolutely convergent. So say if you have a series, it is convergent on it all, but the absolute value is not convergent. So say this one is convergent and this one is with the absolute value is divergent. Then you call that one conditionally convergent. We also have a theorem saying if a series is absolutely convergent, it's definitely convergent. So if you have a convergent series, you cannot conclude that it's absolutely convergent. But if you already have it absolutely convergent, you can conclude that it's convergent. So it's kind of like a pretty kind of obvious thing with termings, but sometimes students make mistake when they think that, okay, it's convergent. And they're like, okay, this series seems positive, maybe it's absolutely convergent as well. But sometimes it's not true. Even though we're not gonna put those tricky things in the exam, but you should know that for a fact that you go from here to here, but not the other way back. Then we have ratio and root test. So the thing with ratio and root test is that the limit that you have to take is different, but the ratio that you use to conclude is the same. So for ratio test, you take limit of n approaching infinity of the absolute value of the n plus 1 term over the n term in the sequence. And then in the root test, you take the limit of n approaching infinity of the nth root of the n term in the sequence. Now, if that limit is more than 1, the series is absolutely convergent. If it's bigger than 1, the series is divergent. And if it's equal 1, this is the important part, it's inconclusive. Now, some of the times the ratio and root test can be interchangeably used. So if what you use one test among these two and it gives you the ratio equal to 1, don't even bother thinking about using the other test. So if you use the ratio test and you have the ratio equal to 1, then the root test is going to give you the same thing. So don't even bother using that. And you're going to see that in the 11.7 strategy, because one of the notes that I put there is that if one test doesn't work, use another one. So just to make sure that if you already use ratio test and it doesn't work, don't even bother using root test, because they're going to give you the same thing. By using another test, I mean maybe you want to try comparison test, integral test, or alternating series test, or even test of divergence. But don't jump between ratio and root tests. Is basically the same thing. Now it's example 3, practice problems 1D. Evaluate the convergence of this series. So the first thing coming to your mind, it should be an alternating series. But let's see where it's leading us. So there are two ways that you can solve this one. First of all, you can say, actually one way only. So this is an alternating series. You can use the alternating series test, but then that one is going to show you just one sign up. So you have the alternating series test is only applicable for a decreasing function. Now if you look at these, you have first of all 0. The Bn term is 5 to the n minus 2 to the n, 4 to the n minus 3 to the n. It's really hard to actually compare n plus 1 minus 2 to the n plus 1, 4 to the n plus 1 minus 3 to the n plus 1. And then you have no idea what the sign is this compared to 4n minus 3n. Well, technically, I would say you can compare these two, but it's going to make life a little bit miserable. So in this case, the one that's going to be helpful is using the ratio test. So the ratio test we use is that we're going to take the absolute value of n plus 1 term over n term. The limit of n approaching infinity of this is going to equal, first of all, it's the n plus 1 term, which is this one, 5n plus 1 minus 2 to the n plus 1, 4 to the n plus 1 minus 3 to the n plus 1. Now this is a to the n plus 1. Now we need a n term and you divided it. So this thing is going to be, this one is actually 8. This one is flipped because you divided that. So you have 5n minus 2n, 4n minus 3 to the n. Now things is easier because now you're gonna take limit of n approaching infinity, right? I'll go down because it takes too much space for the fraction. Now let's look at what is the dominant term in the numerator and denominator. The thing with these is when you look at the series and you have no clue, and especially when it has a lot of power, you can either use root test, but in this case, because you have a difference, it's not like the entire thing to the end, then you're going to use the root test. But in this case, it's something minus something divided by something minus something. The root test doesn't really work, so you're going to look at the dominant terms as well, using the power of n. So if you look at the dominant terms in the numerator, it's going to have 5 to the n plus 1 over 4 to the n plus 1. Multiply 4 to the n over 5 to the n. The rest of the term, because 2 to the n plus 1 and 3 to the n plus 1, is negligible compared to 5 to the n plus 1 and 4 to the n plus 1, as n going to infinity, because you have bigger base over here. Therefore, you can just simple something with the dominant terms. You're gonna have 5 to the n multiply 5 by 4n divided by 4 to the n multiply 4 multiply 5n. So these things cancel out, and your limit is equal to 5 over 4, which is bigger than 1. So our answer is that this one is absolutely convergent. So these are the cases where the ratio test and root test become handy and easier to use than the alternating series test. And again, if you're asking me which one is, when to use which, it's coming from your math intuition. And don't even freak out if you have to do everything twice. Like you try this one and that one doesn't work. It's exactly me when I take math 141. So that's completely normal. Before I go to the next example, is there any questions with this one? Cool. Oh yeah, we have more people joining the group. So Abhi, can I get your PSU email as well in the chat room, please? Thank you. Now is example 4. I'll let you guys work on this one because I feel like it's not hard and it should be pretty, easy to find. So let's give everyone like 30 seconds. If you've maybe like put whatever your approach and your answer in the chat room, so kind of like make this thing a little bit more interactive. All right, I'm just gonna go ahead and do this. Let's see. Yep, the root test. This is gonna be the hints that I would say whenever you guys want to use the root test. For the rest of them, if it doesn't have the m power outside and it looks like a fraction, use the ratio test. So here, yeah, as we said, we're gonna use a root test. Oh yeah, by the way, here it's gonna be absolute conversion by ratio test. And then this one is root test, when you take the nth root of absolute value of an. So it's going to give us n over n squared minus 1. Now, a very clear thing as n approaching infinity. N is approaching infinity slower than n squared. And this one's going to come back to our sessions in, I think, indeterminate form, where we kind of like talk through the relative rate of growth of some of the functions together. N squared is going to be approaching infinity faster than n. So in this case, this limit is going to equal 0, which is smaller than 1. Then it's going to be absolutely convergent by root test. So it's pretty self-explanatory. I'll go to 11.7, strategy for testing series. So this is where we actually put everything together and kind of like when you're given a series, this is kind of like a systematic thing that you're going to follow to, try to test the convergence of that series. So first of all, skim through the question to see if the series can be readily determined for convergence using test of divergence. And this one, remember back in test of divergence is saying, if you take the limit of n approaching infinity of the an term in the sequence and it's different from 0, then you have a divergent series. And a very important note, as I mentioned in that section as well, when you take the limit and it's equal to 0, we know nothing about the series. It can be divergence, it can be convergence. Do not come from here and then say, okay, if the limit is equal to 0, we say it's convergent. That is not right. Or if not, skim through the question to see if you can use any of the simple series that we know, like P series, which is 1 over n to the P. Geometric series when you have geometric series when we have r to the n, which is we have a factor that we just keep repeating in every terms. And then we have telescoping series where you have most of the terms cancel out one another. Or we can use alternating series test. As you see in the alternating series test, it's really easy to use as long as you can prove that a series is decreasing and also limit of n approaching infinity of the n term in that sequence is equal to 0. Yeah, and then the second step, if those things doesn't work, is when you come to try to use, if the n term is kind of complicated, choose the test based on the form. If you have rational function, use either comparison test or ratio test. Why comparison test? You can see as I did last week when we have ratios and we can add or minus something to compare it with one of the series that we already know, like a p-series or a telescopic series, or no, not telescopic, a geometric series. All this week we learned about ratio test. So if it's in a rational form, we can also use ratio test. And of course, if you conclude that it's absolutely convergent by ratio test, the theorem allows you to say it is convergent because an absolutely convergent series is also convergent. If it's raised to the power of something, like to the n, then you use a root test. If it's easily integrable or none of the other tests work, so the last result is going to be integral test, and usually it's related to log and ln, because for these things it's really hard to compare with log. So you're gonna use integral test. So it's gonna be your last result, and we already seen it in integral test. The conditions that we need to satisfy is more complicated, and it's usually take more time to take the integral. Again, in the integral test, notice that the sum of the series is not equal to that integral that you take. There's just some association between the convergence of these two, but those are not equal to one another. So when you take the integral, it doesn't equal to the sum of that complicated integrable series. Now the third step, as I just give like a quick briefing before, if one fails, try another one. And this one is when you if ratio test doesn't work or root test doesn't work, don't try if ratio test doesn't work, don't try the root test, because those two are kind of like a little bit similar to one another. So it's just gonna waste your time and not giving you any new information. Number 4, be careful on what the question asks. So this is where it comes the tricky thing about absolutely convergence and just simple convergence. If it's only simply convergence, you can use any test and just prove on the convergence of that series. However, if it's asking about the absolute convergence or conditional convergence of the series, then you have to test both the series and the absolute value. But if you can prove that the absolute series is convergent, then it's absolutely convergent. However, as I say, the case of conditional convergence is that when you prove the series this one is convergent, but this one is divergent. A very clear thing is that when you see this series, -1 to the n over n, when you have itself, the alternating series test prove that this one is convergent. But if you take the absolute value, it's going to become the harmonic series 1 over n, then it's going to be divergent. So this series is conditionally convergent, CC. So that is one of the very clear example for that. Let's do, I also have, before we do the example, I also have the table to maybe categorize everything together. You have a test, you have the conditions that you need to satisfy to use that test, the conclusion it allows you to make, and some of the warnings that I kind of mentioned through each of the sections. So I put everything together here, and I'll send the slide to Dr. Kasher after these sections. I also have her step to find the absolute and conditional convergence of a series here. So let's go to the example. So determine if each series is absolutely convergent, conditionally convergent, or divergent. Now the first one, let's say, so in this case, you don't need to go through the entire full problem. So we can just maybe propose something to do in these questions. So first of all, let's start it with the first one. What test do you think I should use for the first one to talk about the absolute and conditional or convergence or divergent of the series? Yep, that is going to be test of divergence. Yeah, I think you guys are getting there, getting the math intuition. So you have 3n over 5n plus 1. So it's going to give us 3 over 5, which is different from 0. So you conclude that this series is divergent. Note the fact here that your series, so the series of itself is equal to the absolute value. So you only need to do this one once when you have a series is divergent. However, in some case, like the one that I just mentioned, -1 to the n over n, this one is not equal to its absolute series. So that's why this one you have, this one's convergent, but this one is divergent. Here, both of them are equal to one another. So if one is divergent, the absolute thing is divergent. The entire thing is divergent. Because the series is equal to the absolute value of itself. Now for number 2, what do you think that we should use? Here is actually -1 to the n, multiply e to the 1 over n divided by n cubed. So this n is not in this thing. Yep, AST is only 1. Look at what the question is asking, right? The AST only allows you to make conclusion about the series itself. But what about the absolute series? Because if you want to prove that the series is absolutely convergent, you have to consider the absolute series, which is just this part, right? So by alternating series test, and I would say if you work out the questions, then it is a decreasing function as well. So you're gonna the series is convergent by alternating series test. Yep, you can use ratio as well. Let's see what the ratio is going to give us. N approaching infinity, absolute value of the n plus 1 term over the n term. It's going to give us limit of n approaching infinity. E to the 1 over n plus 1 divided by n plus 1 cubed, multiply n cubed divided by e to the n plus 1. Now, the thing with this is that as n approaching infinity, the dominant term here is n cubed and n cubed here. So this ratio is going to give us 1. So what we have left is limit of n approaching infinity. E to the 1 over n plus 1 minus 1 over n. Right? So this one is starting to get complicated because now you have to consider what power is this thing heading to. So you can use the ratio test and continue to think about to solve this. Wait, hang on. What is it? Here's the chart. And we plug in values for n to make it easier to find the ratio. You can, but I mean, you don't know what value is the representative one. So some of the thing with the this series is that I would say not just this series, but maybe some like in the general case, plugging n in will help if you plug in the right value of n, and if you have to plug like 5 or 6 of them to make sure that it follows the trains that you think it is. So yes, you can definitely plug in value of n to make it easier to find a ratio. That is true, but make sure that you include enough values. So say plug in 5 or 6 value of n, so to make sure that your train that you think it's going to is the correct one, and not just for some specific values. So some of the series is like it's initially increased, but when n approaching infinity, essentially it's decreased. So when you plug in values, maybe you are stuck in somewhere here or somewhere there. So make sure that you plug in 5 or 6 of them to make sure that you see the train. In this case, I would say we have as n approaching infinity, 1 over n plus 1 is smaller than 1 over n, right? So when you have 1 over n plus 1 minus 1 over n is smaller than 0. And if you put this one is actually equal to 1 over minus 1 over n plus 1 multiply n. If you use the same denominator and solve for it, this one is -1 over n multiply n plus 1. So this one is going to give us limit of n approaching infinity, e to the -1 n multiply n plus 1. This thing is approach 0 as n going to infinity. Therefore, you have e to the 0, which is going to give us 1. That's why here the ratio test wouldn't work. So I'll put the red thing here. Ratio test inconclusive. So, okay. Before I solve this question using another way, that's gonna give us some answer. Is there any questions with why is it inconclusive? What I did from here to here is basically when you have, I just replaced 1 over n plus 1 minus 1 over n, because you're going to have, this one is going to be n over n multiplied n plus 1 minus n plus 1, which is going to give us negative 1 over n multiplied n plus 1. So from here to here, I just do this replacement. And so if you look at the train as n going to infinity, the entire of this fraction is going to 0. So e to the 0 is going to be 1. That is the limit, because the ratio that you find using the limit that you find using ratio test give is equal to 1, so it's inconclusive. So when it's inconclusive, another way of we solving it is that you're trying to, let's look at the final purpose. You try to determine the convergence of the series of e to the 1 over n cubed, right? Let's see the rational, as I said, the rational function, you have two ways to use it. You can use ratio test or comparison test. So in this case, I'm going to use comparison test. First of all, your series here is always positive because it's e to the something divided by n cubed. And if you look at this, as n going to infinity, this value is always going to be smaller than or equal to e over n cubed, right? And this is the p series. The p series is 1 over n cubed. This one is basically e multiplied this series, right? And this is a convergent series. So when e multiply a convergent series, it's still a convergent series. That's what we have, I think, in early in the, I think 11.2 sections when we talk about series and the property. Therefore, this one, and so this one is the convergence by p series. Therefore, the thing inside is also convergent by, this one is convergent by direct comparison test, because you compare it with a convergent series. So the series itself is convergent and the absolute of it is also convergent. Therefore, we conclude that it's absolutely convergent. Is it clear here of how I get over there, get to this point? So when you have a fraction and you use ratio test, but it doesn't quite work or it's kind of hard to use, maybe you might want to consider the comparison test. So is it clear here? Okay. So it's AC because you compare the absolute value of the original. That is true. But how did you get AC? Okay, hang on. I understand how you got e to the 0, but that equals 1. Okay, so it's inconclusive here. So at P, what I did is that because it's inconclusive here, when we use ratio test, so I end up not using ratio test, but I use direct comparison test for the absolute value of the original. So you use the direct comparison test with the absolute value here, right? So that's how I get the absolutely convergent. Is it clear of how I did it, or you want me to explain more? So what happened here is the ratio test is, okay, cool. Let's do number 3. The series of 2 plus cosine of n divided by 3 to the n. Let's see what you guys think we should use here. Yeah, please tell me that in the chat room to say what you guys gonna use for that series in number 3. Happy, you're using comparison test. Kyrie, can you tell me why we use AST? I mean, I haven't said it's right or wrong yet, but you have to have reasons for your decision, right? Why do you use AST for number 3? cosine is oscillating, but look at the numerator. What do you have? You have 2 plus cosine of n. Is it oscillating anymore? The alternating series test is alternating series is where you have one term positive and one term negative. When you have 2 plus cosine of n, because cosine of n is smaller than 1, and squeeze between -1 and 1. That's why, yes, that's why this one is always bigger than 0, actually even bigger than 1, and smaller than 3, right? Therefore, you cannot use alternating series test because it's not an alternating series. See? That's why one of the things that I always want you guys to check with the conditions. Like, if you look at the tables here, the alternating series test, I note the fact that the condition that you have to satisfy, it has to be alternating first, and then the other one is that it's decreasing in the other thing. So first of all, check if it's alternating series. So in this case, we don't use alternating series test because it's not an alternating series. We're gonna use, and then this is a ratio. So you can either choose to use ratio test or comparison test. Here I would use comparison test. Why? Because when you try to take cosine of n plus 1 using the ratio test, it doesn't really give you anything helpful because you have no idea what's cosine of n plus 1 as n going to infinity, right? So therefore, I'm going to use the comparison test here. And you already have the number so that you can conclude, so that you can compare. 2 plus cosine of n over 3 to the n, smaller than 3 over 3 to the n, right? This one is a convergent series by trigonometric series with the r value equal to 1/3. Therefore, this one is also convergent by direct comparison test. Now, is it conditionally convergent or absolutely convergent? Well, let's just think about it. This series is always positive, right? So the series 2 plus cosine of n over 3 to the n is equal to its absolute value because it's a positive thing. So when you have a positive series, it's always equal to itself. Therefore, it is the absolute value. It's also convergent, right? Because it's just equal to itself. Therefore, a conclusion is that it's absolutely convergent. So is it clear to everyone how I get absolutely convergent from this convergence? It is because the series is equal to itself. It's just similar to 1, right? Yep. Okay, cool. What if it's 0.5 plus cosine? Now, if it's 0.5 plus cosine, the way that you're gonna solve this is going to be, it is true that it's gonna be one term positive and one term negative. In that case, you're gonna have one term is gonna be half, and then one term is going to be, it's gonna be one term is gonna be -half, and the other term is going to be 3/2. Oh, excuse me. In this case, let's see, half, and then 3/2 divided by 3 to the n, and then 3 to the n. In that case, I say you have to, you can use alternating series for that one. But then you have to put it in the form that you can use alternating series. So for sure you can prove that it's alternating. But then you have to maybe take the derivative to conclude that it's it can be conditionally convergent. That is true in that case. Using alternating series test, you're gonna have maybe a decreasing series, and then it's then you have the then you have limit of n approaching infinity also going to 0. So it's convergent by alternating series test. Yeah, right. That the numerator can be negative. Yeah, it's actually half of the way is going to be negative and half of the other way is going to be positive. But in that case, I would say I honestly have no idea how to solve that one yet, because that one is going to require more than what you've learned so far using all these tests, because then you're going to need one extra sections of how to derive the series, like how to put that in the form, maybe like to the end of something. Try to, like, the way we're going to do that is that we're going to try to eliminate cosine and put everything in terms of power series, which is going to be the focus of exam 3 or like final exam. So yeah, we're going to need the extra piece to solve the cosine. You're going to actually see it in exam 3, where you try to represent cosine as some power functions, and it's going to make everything in the terms of n, and it's going to make our life easier to solve. Okay, cool. Yeah, using the DCT to find the absolute convergence, basically you're just gonna compare the absolute value of the original. So say you just consider the absolute value of that series, and then if you compare it with something and you prove that that absolute series is convergent, then you can conclude that it's absolutely convergent. That's why I go over the definitions of absolutely convergence in the beginning. Is that a series is absolutely convergent if its absolute series is convergent, right? So as long, it doesn't really matter how you solve it. Like even if you use the integral test to conclude that the absolute series is convergent, the series is still absolutely convergent. So the way that you prove it doesn't really matter, as long as the thing that you consider is the absolute series. You see what I'm saying? Okay. So having said that, we also have exam question 4 and 5. So 4, I would say it's kind of like very self-explanatory to you guys. Is that first of all, the series. First of all, it's cosine of n pi over square root of n. So I think we did one of the examples similar to this. It's gonna give us the hint that it's alternating series. So if you write down the terms, it's going to be for m equal to 1, it's going to be negative 1 over square root of 1, and then 1 over square root of 2, negative 1 over square root of 3. So the series can be equal to the series of negative 1 to the n divided by square root of n. So this one is going to be convergent by alternating series test, but this one only itself, as you see, is an alternating series. So the series is convergent by alternating series test, but you have to consider the absolute value. So the absolute value is 1 over square root of n, and this one is going to be the absolute value is divergent by p series, because the p value here is n to the half, right? So p is equal to half, which is smaller than 1. That's why it's divergent. And so in this case, we conclude that it's conditionally convergent, because the series is convergent, but its absolute value is not convergent. So it's conditionally convergent. Another way you can do this is that some of you might try the ratio test, but if you do that, you're gonna see that it's gonna give you the ratio equal to 1. Therefore, it's inconclusive. Limit is going to equal to 1. That limit is going to equal to 1, so L equal to 1. So that is not going to be helpful for 4. But then, as I say, you always have the comparison test to use, right? And then also some other thing, like P series here that we're using, or even if it's trigonometric series or harmonic series or telescopic series, you can always use those to conclude about the absolute series if that series is simple. Like here, 1 over square root of n. Take the absolute value. So the absolute value of these, so I rewrite this one is the series of negative 1 to the n over square root of n, right? And so the absolute value of this is just going to be 1 over square root of n. So first of all, is that part clear to you? Of how I get the absolute value is 1 over square root of n. Okay, if that one is the absolute value, right? Now you look at this as the absolute series, and you're trying to find, because you already have a series like the original series is convergent, right? But you have no idea about the absolute one. Therefore, you look at this series and you try to find if this one is convergent or divergent. If it's also convergent, the series is absolutely convergent because the absolute value is convergent, right? But if it's divergent, then you're gonna conclude that it's conditionally convergent. Here, you look at this series. This is the series that we learn when this is the one of the form when we have the P series. So P series is 1 over n to the P, and it's going to be convergent when you have P is bigger than 1, and then divergent when P is smaller than or equal to 1. Here P is half, which is smaller than 1. Therefore, we conclude that it's divergent. And I didn't take any test at all. It's just by P series. So it's not as complicated. How is it convergent by AST? Okay, so we have the AST have unit is to be decreasing and limit of n approaching infinity, right? So let's look at this. So this one, do you want me? Okay, cool. So let me go to the last one. So number 5, here we have another alternating series, and it has the power of n. So 2 ways you can do this. As I say in the strategy, if you have something to the power of n, usually it's going to be root test because you're going to try to eliminate that n power. So let's do root test on this. Limit of n approaching infinity, and we're going to use another test if it doesn't work out, but let's try to use a simple one. So you take the n root of the absolute value. The absolute value is 3n minus 5 divided by 4n plus 3, right? So you have limit of n to the n approaching infinity. The nth root, so what we have is 3n minus 5 divided by 4n plus 3. And as n going to infinity, this one's going to give us 3 over 4 based on just the dominant term in the numerator and denominator. And here, because the highest power is the same, so you only care about the coefficient in front of the dominant terms. So it's going to be 3 over 4 smaller than 1. So it's going to be absolutely convergent by root test. So is there any questions so far? Okay, if not, I'm just gonna go ahead and wherever we see a negative 1 to the n, what should we do? Okay, when you have negative 1 to the n, right, what does it give us? First of all, it's an alternating series, right? So you can either use the alternating series test. I would say a very good way is to always use the alternating series test first before you try to determine the absolute value. Why? Because if you determine the absolute value and it's divergent, but then you have to use the alternating series test itself to find the convergence, right? So I mean, you can either consider the absolute value first. Alternating with root or ratio is crazy. That's one of the way. Not just root or ratio. You can see in like the previous question, right? I use the direct comparison test as well. So here, I use the direct comparison test. So I would say, okay, let's think about it. If you have negative 1 to the n of something, it's an alternating series. That's for sure. Let's consider the absolute value of the series first. So you consider the absolute value. If you have it divergent, then you can continue to use alternating series test to solve to test the series itself. But if you have it convergent already, then you conclude that the series is absolutely convergent because the absolute value is convergent, right? So I would say, first of all, consider the absolute value, the absolute series first. Then if it's divergent, use the alternating series. But if it's convergent, you can immediately conclude that it's convergent. Whatever test you use, depending on the form, like as I say, if you rational or fraction, you can use comparison test, ratio test, or and also p series or geometric series to compare it with. Is it clear? So first of all, always consider the absolute series. Yeah, I apologize for I should have just considered the absolute series first. But if you just consider the absolute, you're gonna have its divergence anyway, and so I will have to continue to go with convergence in number 4. But generally, the approach is first you take the -1 over multiply some terms bn. First of all, always consider what is this series? Is it divergent or convergent? And then you come to this one. So this is number 1, this is number 2. Are we good here, or is there any questions? Yep. Yeah, no worries. I have some notes for next week. Next week is exam 2 review. Please do your practice exam questions so that I can pick out problems to solve for you. But then at the same time, try my practice problems. So I would say if you see like my practice problem is way too hard, or you like finish halfway already and like it takes you so much time, you can leave half of the other half there and work on the practice exam first, because the practice exam is like the closest resources for your exam like level. So work on that first, and if you work on the practice exam and you have some questions, email me. And then if you want me to solve my practice problem as well, please email me as well. Make sure that you do that as early as possible, because I need to write down the solutions on that and then put all the solutions together. I don't carry the solutions with me when I travel here and there. So I need time to write them out, and so just some more time to prepare for the exam review next week. And then here you're gonna see I have like massive examples for you to finish. So I think I put like 1, 2, and then 3 is going to from A to Z, A to R, and then in number 4, 5, and then 6, 7. So it's a lot for you to finish. So don't freak out if you don't finish. Just work on a few of them, maybe like pick 1 or 2 in each questions, just to make sure that you familiarize yourself with all types. I would say I didn't have any repetition in my practice problems, but yeah, so that it doesn't bore you out. But if you don't finish it, don't freak out. That's all I want to try to say. Yeah, that's all I have for today. I'm gonna send the slides to Dr. Kasha, and the video I'm gonna upload it shortly. So I'll see you guys next week. Have a great weekend, guys.